Following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmayo@ybcc.edu and I'll respond as soon as I can. All right, so today we're going to start Chapter 4, and we're going to take a look at Section 4.1, which is solving systems of equations by graphing. What is meant by a system of equations? Well, we've looked at linear equations and we've graphed single linear equations on a graph and we got a straight line. Now we're going to be looking at a system where we'll have two linear equations. We'll graph them on the same coordinate plane, and then we'll look to see what the results are. Okay, there are three different possibilities. So let's take a look at the first one. One possibility is that the two lines intersect at a given point. That point would be the solution to the system. This is known as a consistent system, meaning that it has a solution, and we say that it has independent equations. All right, so the system is consistent, meaning that it has a solution, and the equations are independent of each other. All right, that's one situation where the two lines intersect at a single point. Let's look at another possibility. Here we have a situation where the two lines are parallel. This is known as an inconsistent system because it has no solution, but the equations are still independent from one another. A final and third possibility is where we have two equations, but they are in fact the same line. We just have different versions of the equation. This is known as a consistent system, but the equations are dependent equations. That is to say, they're dependent on one another. So three possibilities. One, the two lines intersect at a given point, and that the coordinates of that point would be the solution of the system. We say it's a consistent system because it has a solution, and the equations are independent of each other. Second possibility, an inconsistent system where the lines are parallel, so they do not meet, they do not cross, there is no solution, but the equations are still independent from one another. Finally, the two lines are in fact the same line, so it does have a solution. In fact, the solution would be all points on the line, so it's a consistent system, but we say the equations are dependent. They are not independent of one another. They are in fact different versions of the same equation. All right, so what we're going to look at now is some systems of equations that we're going to solve by graphing. Let's see here. So let's go to a new rectangular coordinate system. It says solve each system of equations by graphing. All right. Our first equation is y equals 3x plus 6. Our second equation is y equals negative 2x minus 4. So let's take a look at the red equation first. To graph it, let's find a couple of ordered pairs. So in fact, we don't have to, but we could use the X and Y intercepts. So I'm going to do that for this first one. So if y is 0, we would get 0 equals 3x plus 6, subtracting 6 from both sides. 3x equals negative 6. Divide by 3, we get x equals negative 2. If x is 0, we get y equals 3 times 0 plus 6, so y equals y equals 6. So negative 2, 0 is right there. 0, 6 is right there. So let's graph the red equation. Let's see here. Right. Now the blue equation. Let's see. We could again go ahead and use the X and Y intercepts. When y is 0, we get 0 equals negative 2x minus 4. We'll add 2x to both sides. 2x equals negative 4. Divide by 2, x equals negative 2. If x is 0, y equals negative 2 times 0 minus 4, y equals negative 4. Negative 2, 0 is right there. 0, negative 4 is right there. And let's see here. Okay. All right. Now, what I've done is I changed the point of intersection and made it purple. If you know your colors, you know that if you mix blue and red together, you get purple. So the point of intersection would be purple because that point is both red and blue. All right. And labeling that point, the coordinates are negative 2, 0. So that would be the solution point, the point where the two lines intersect. Now, a way that I can check this is to take that point and plug it into both equations to see if it works. Well, as it turns out, in this case, I already found that point in both equations, so I don't need to go back and double check it. But it doesn't always happen that the point of intersection is one of the points that you use to get the lines. All right, let's take a look at another example. And let's see here. We have 3x minus 6y equals 18. And x equals 2y plus 3. All right. Again, I'm going to go ahead and use the X and Y intercepts. So if y is 0, I get 3x minus 6 times 0 equals 18. So 3x equals 18, x equals 6. If x is 0, I get 3 times 0 minus 6y equals 18. So negative 6y equals 18. Divide both sides by negative 6, y equals negative 3. 6, 0 is right there. 0, negative 3 is right there. So let's see here. Lining this up with this ruler I've got is not easy. while I'm thinking of it. So to do these problems in WebAssign, all it asks for is the solution. It doesn't give you a graph and ask you to graph on it. So you'll need to get some graph paper, and you have a couple of options. One, you can go to one of the local stores and purchase a pad of graph paper, or you can go online and just Google graph paper. There are various websites. Some of them have the graph paper you can print off. Some of them even have the X and Y axes already on them. But you'll want to create graphs kind of like these blank ones that I'm using, and then be careful that you are accurate. Use a straight edge, line up your points so that you can find the point of intersection if there is one. But you'll need to do that. Like I say, WebAssign for this assignment just has you put in the ordered pairs or ordered pair solution, or write no solution. Okay, let's see here. We're looking at the blue equation. Okay, again, let's go ahead and use the X and Y intercepts. See, I don't need that to be quite so long. If Y is 0, X equals 2 times 0 plus 3, X equals 3. If X is 0, 0 equals 2Y plus 3, subtract 3 from both sides, divide by 2, Y equals -3/2. All right, so 3, 0 is right there. 0, -3/2 would be right there. Okay. It looks like they're parallel, doesn't it? Yeah. So if they're parallel, there would be no solution. Okay. The lines don't intersect. How could we verify that they're parallel? Well, we could come up with evidence that they have the same slope, but different x-intercepts or different y-intercepts. We could put them in slope-intercept form. Let's do that. So I'm going to take this first equation and put it in slope-intercept form. So I'm going to solve for y. So I'm going to subtract 3x from both sides. I'm going to divide each and every term by -6. Y equals 1/2 x minus 3. So that says the slope is 1/2 and the y-intercept is -3. Well, here's a y-intercept of -3 and a slope of 1/2. Okay, let's take the blue equation and let's put it in slope-intercept form. Let's see. Well, let's see, the quickest way to do this, I guess I'm going to subtract 3 from both sides. So I've got that, which is the same thing as that, right? Just switching the sides around, then dividing by 2, y equals x over 2 is the same thing as 1/2 x minus 3/2. So the y-intercept is -3/2, and the slope again is 1/2. So I have the same slope, so the lines are parallel. They have different y-intercepts, so they have to be different lines. No solution. All right, let's take a look at another example. This is x plus y equals 1, and y equals x plus 5. Okay. Again, I'm going to stick with the intercepts. They seem to be working just fine, so why not? Let's make this a little shorter so I have more room. All right, if y is 0, x equals 1, If X is 0, Y equals 1. So 1, 0, and 0, 1. See here. So there is the red line. Y equals X plus 5. If Y is 0, 0 equals X plus 5. Subtract 5 from both sides. X equals negative 5. If X is 0, Y equals 5. Negative 5, 0 is here. 0, 5 is there. So let's draw this line. It appears as though the solution is what? Negative 2, 3. Let's check our work. Let's plug that in here. If X is negative 2 and Y is 3, we get 1 equals 1. Oops. 1 equals 1. So it checks. If X is negative 2 and Y is 3, we get 3 equals negative 2 plus 5. 3 equals 3. So it checks there as well. So the solution to the system is the single point, the ordered pair, negative 2, 3. Okay, let's see here. Let's take a look at another example. This says 2y equals negative 6x minus 12. And the second equation is 3x plus y equals negative 6. All right. So finding the X and Y intercepts here. If y is 0, I get 0, 2 times 0 rather, equals negative 6x minus 12. So 0 equals negative 6x minus 12. I'm going to add 6x to both sides. 6x equals negative 12. Divide by 6, x is negative 2. If x is 0, 2y equals negative 6 times 0 minus 12. 2y equals negative 12. Divide by 2, divide by 2, y equals negative 6. So negative 2, 0, and 0, negative 6. Okay. So there's the red line. And now the blue line. Let's see here. 0, 0. If y is 0, 3x plus 0 equals negative 6. 3x equals negative 6. Divide by 3x equals negative 2. If x is 0, 3 times 0 plus y equals negative 6. Y equals negative 6. So negative 2, 0 there, and 0, negative 6 is there. What do we have? We have the same line, don't we? So the system would be all points on the line. And at this point, we'll say infinite infinitely, let's see if I can spell here. Infinitely many solutions. Okay. And that would be what? All the points on the line, because it's basically just two equations that are in fact variations of the same equation. All right, so we've got a situation where there's infinitely many solutions. We've got a situation where the lines are parallel and there's no solution. And we've got situations where there's a single point of a solution. Okay, well, that's it for today. I'd ask if there's any questions, but there's nobody else here. So have a great rest of the day. And I'll be back at 1:15 with an office hour, should you have need of me.